Data Skeptic features interviews with experts on topics related to data science, all through the eye of scientific skepticism. Our topic for today is logistic regression.
All right, quick update. Actually, it's a correction. Well, sort of a correction before we start. Linda, do you recall a little while ago you had said when I was talking about the Poisson distribution, you said, oh, that means fish.
Yeah, you told me that someone sent in a note. And of course I was right because I took French.
Yes, we got a correction. So thanks to @AloriMD who wrote in and let me know that Poisson does mean fish in French. But in my defense, the Poisson distribution is named for Simeon Poisson, a guy. So his last name is Poisson. I don't think that makes his last name translate to fish.
Maybe he was a fisher person.
But I was pretty indignant in telling you that it wasn't Poisson.
I know. I didn't want to correct you on your own show, so I left it to your listeners to correct.
Oh, great. So thanks for letting me put it out there.
Yeah.
Well, anyway, last week we were talking about dropout, and we're going to have a lot of deep learning topics in the coming weeks and months to come. That's going to be a big focus of the mini episodes in 2017. So in order to get into deep learning, I thought we should take a step back, actually, and talk about a much more simpler method that helps provide some of the baseline for what deep learning is all about. You know what deep learning is?
You know what? Kyle has mentioned this topic to me many times, and he actually has a book right now on one of our side tables that says deep learning.
Yeah.
And no,
have you been reading it?
I don't know what deep learning is. I just saw the title.
Well, we're going to get into it bit by bit because it's hard to jump into all at once. And we're going to start by talking about logistic regression. Logistic regression is very similar to linear regression that we've talked about before. So I want to start there and talk about home prices also because our big episode on the open house project should be coming out in just about a month's time. So we're going to be doing some regression on that data. But if you had to guess how one arrives at the price of a home, what are some of the things that go into it?
Well, how big is the home?
Square foot.
How many bedrooms, bathrooms? What area, location is key.
Yep.
How old is the home?
Right. So these are all good features that we'd like to use. Let's stick to the three basic ones: number of beds, number of baths, and square footage.
Well, location.
Yeah, that's important. You have to quantify it, though, in some way, and that's a little tricky. It definitely matters, obviously. But let's just say home buying was very simple. Oh, and also you throw in an intercept, which is sort of the baseline price of any home. The point being, we have a model of how this should work. It's W1 times the number of bedrooms plus W2 times the number of bathrooms plus W3. Just keep adding weights to all these different features you have, right? Now, coming up with the best weights, the best parameter values, that's what logistic regression is going to help you do. We're now actually at the point here where I think this is as deep as we go on Data Skeptic mini episodes. I would love to talk about Wilks' theorem and the quasi-Newton method and some stuff like that. I don't know that that goes great over the air. The objective we want to get into is what is logistic regression, not how do you do it. There's good material already in existence on how. So what is it? It's the process of doing linear regression, finding through maximum likelihood the best values of those parameters to suit your model. And so what the algorithm will do for you is find the best possible values given your input data. But that would be for like linear regression if you wanted to determine the price of the home. So logistic regression takes that one step further by applying your output to a logistic function, which is a special type of curve. And I sent you a picture of it if you want to pull up that email. And this will be in the show notes too. It's basically just a way of mapping any data, any numeric value, into a confined range between 0 and 1. Do you see that curve?
Mm-hmm. Looks like an S.
Can you tell what its minimum and maximum values are?
Y-axis goes from 0 to 1.
Yep.
And on the x-axis goes from -6 to +6.
And that's just on the one I showed you there. Actually, it could go negative anything to positive anything. So the nice part about the logistic function is it maps any numeric value to that range 0 to 1. And it maintains like the ordering and stuff like that. It also kind of spreads out the data that are near 0. So the difference between two really big numbers will be very small, whereas the difference between two small numbers will be kind of big. So that's very useful to help the machine learning algorithms find the solution faster. So I wanted to do a project here. I wanted to kick something off that we're going to work on probably this whole year and make little improvements to it. And, we're an audio podcast, so it's hard to do some visual stuff. So I thought, wouldn't it be cool if I built something that listens to this podcast and decides who's speaking, me or you?
Okay.
Well, I expected a bigger reaction out of you. Can you maybe act really impressed?
Wow. I had problems distinguishing our voices. I didn't know when you were talking, it was actually me.
Yeah, a lot of people write in. They say it's very confusing. They can't tell who's talking. So this is going to be a really great project, clearly. I took a first stab at it this afternoon. Now, let's talk through how I did this. I sent you another image there. Can you describe what you see? Maybe say the name of that thing if you know what it is.
I don't know, but it looks like little wavelengths. Like, when an earthquake happens, looks like that.
Yes, so you're describing waveforms. Can you tell in the picture you see there, and I'll include this in the show notes too, which one of us is speaking? The first line or the second line? Which is you?
Well, I don't know. They don't give it X and Y axis. How am I supposed to know what it means?
Oh, so good question. The X-axis is time, and the Y-axis is amplitude, meaning how loud the sound was at that moment.
Well, on average, you're louder than me. So I feel like maybe you're the top. Is that true? Or you're the bottom? The bottom has more range, which to me signifies volume. So the bottom person their max volume was greater than the top person. But the top person looks like on average was louder generally.
So what's your final answer here? I can't tell.
I don't know.
Just guess. It really doesn't matter.
It matters to me.
You don't have to overthink this. It doesn't matter.
It matters to me. Hold on.
Or we're keeping score then. I'll tally it up at the end of the year. How many of these arbitrary guesses you get correct?
I want to be smart, so it matters to me.
Okay.
Okay, you're going to be the bottom one.
Final answer?
Fine.
Wrong!
Man, I had it right the first time, but you then
did.
gave me this vicious look, and I switched it. Kyle tricked me.
Yeah. Well, it's actually a little bit unfair of a question because the reality is you can't really tell who's talking from a waveform. I mean, you might in a tricky way, like, oh, Kyle talks more, so that one must be him, or he shouts a lot, so that must be him. There could be some clue like that. But in general, when you talk pretty evenly and you normalize it as I do in post-production, then people's waveforms pretty much look the same. However, as you were pointing out, people can tell the difference between our voices, right?
Oh, yeah.
Yeah. So what is it that the human ear is doing that maybe we can mimic in a machine learning algorithm?
I don't know.
What's the difference between your voice and mine?
Well, ours is connected to our brain. So our brain is actually interpreting. So it's like picking up the emotion.
Mm-hmm.
Just your exact mood and tone and all those things that humans are actually genetically programmed to pick up.
Yeah. So I like where you're going with this, mentioning the brain, because ultimately, I'm going to solve this with deep learning. And we're going to get to that in future episodes. But I wanted to do a quick and dirty thing because we just had yesterday afternoon to put together the show. I wanted to use logistic regression. So what I did, I used the fast Fourier transformation. And look, we can't do a mini episode on everything, okay? So if you want to learn about FFT, go check the dataskeptic.com blog, because this week I'll put up a bunch of stuff for anyone that doesn't know what it is, so you can learn about FFT. But basically, FFT converts a signal from the time domain, as we see here. These are the amplitudes of our speaking through time, and it converts it into the frequency domain, so we can see the different tones your voice uses.
Okay.
What's your understanding of the word frequency in this situation?
Is that volume?
No, it's distinctively not volume.
What is it then?
Frequency is like pitch. So even though we're not singing, we're not being like C, 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 or whatever. Yeah, well, even without tuning and singing and all that, we're still saying pitches, right? Our voices are still at certain levels.
Sure.
And mine is very masculine and pretty tough and awesome voice,
And I'm an alto.
Now, voice is also very complicated. If you scroll down, the other thing, and again, this will be in the show notes, on the left are some more waveforms, and on the right are their frequency spectra. The top one there is that's your frequency spectra, and the bottom one is me. Now, can you tell much difference between those two, the top red one and the bottom red one?
Well, since I've been taking vocal lessons, sounds like my voice has more dynamics. I'm just kidding.
Maybe. There are, visible differences in our frequencies of our voices. So I thought, hey, without looking into the real things that make us different, like the timbre of our voice or our cadence and different things like that, can I just do kind of a cheat? Can I do this quick and dirty, predict is it Linda or is it not Linda, meaning is it Kyle? And can I do that just by frequencies alone? So what I did, what do you think? I mean, we're talking about it, so obviously I did it, but how successful was I?
I mean, I don't know. There isn't enough data for me to feel like I know what's going on.
Well, guess what kind of accuracy logistic regression might give us?
It looks like at least 50%.
Better than that. I got 84% accuracy.
Wow.
Now, there's a couple of caveats here because I'm not yet convinced. I'm still a little skeptical. I may have overfit this data if the regression is picking up on some artifact of our recording. Like we use different mics, you and I. And maybe there's something about the frequency spectra that it's sort of cheating in a way. You know, it's picking up an artifact because this should work no matter what microphones we use in theory. At least that's the goal. I don't want to just detect the hardware. I want to detect our actual voices. So I got a little bit more digging to do. Keep your eye on the dataskeptic.com blog. I'm going to post a lot of cool stuff about how I did this feature engineering and stuff like that. When we started talking about regression, it was in terms of houses, right? And there were obvious things like the number of bedrooms, number of bathrooms. What do you think I used as my features to describe our voices?
I thought you said pitches.
You're right. I did use pitches, but do you have a sense of how I used it in like a formula?
No.
Well, I did. In the first example, it was beds times a weight plus baths times a weight. I end up breaking down that frequency spectrum into little buckets. And I said, from this hertz to some upper hertz, that's the first bucket. And then I made the second bucket and so on and so forth.
So how did you pick these buckets?
So first thing I did was I trimmed down the whole frequency spectrum to anything under 1,000 hertz. Here, I'll put in a tone right here of what 1,000 hertz sounds like. So that's a little bit high pitched, right?
Yeah.
And our voices, even though they do resonate above that, we don't talk in that high of a pitch. So I knew all that information is not going to be very useful. So I trimmed it down and then I made some little buckets and I experimented with this and I ended up coming down to 10 buckets. So like 10 little bands that are just calculating how much of that frequency appears in each of our voices. So then each of those bands is a numeric value that describes our voices. And what I'm asking the logistic regression to do is to say, hey, if I tell you the values of how much of these frequency bands were being used, can you tell me who the speaker is?
Of who's most commonly in that bucket?
Yeah, pretty much, yeah.
Oh, okay.
So then what it does is each of those gets a weight. In the buckets where it's most characteristic of my voice, since I'm trying to predict, is it Linda's voice or not? If it's my voice, then it goes negative, right? Because it's like, no, this is very un-Linda-like. And in the buckets where your voice typically shows up, it goes positive because they're very Linda-like. And the spectrum where either neither of us speak or we both speak, those end up around 0 typically. So yeah, this ended up, if you go to the show notes again at the site, you can see one of those bands is very characteristic of saying this is probably Linda's voice. So that's what it latched on to. So how logistic regression solves this then is it finds the optimal weight for each of those bands, and then it maps it through the logistic function, that S-curve, to say, is it towards a 1 or a 0? And you just select a breaking point that says above this, it looks like it's Linda. Below it, it looks like it's Kyle.
So now I just think I should start talking in your podcast really funny, like, hello, like that.
Yeah, and that would screw it up pretty bad. Yeah.
And then I could confirm it was an overfit.
Or maybe we can try and trick it. Maybe you talk like me and I talk like you. Let's do that for a minute. You pretend to be me.
I'm Kyle. That didn't work.
Hi, I'm Linda. This is how I talk.
This is Kyle Pulich.
I'm gonna go do yoga and sit with the bird.
Sit with the bird.
You're not doing a very good impression of me.
I'm not hearing myself in you.
All right. Well, I'm gonna work on my impression of you. You work on your impression of me. Everyone who's listening should go to dataskeptic.com, check out the show notes for more details on this, because this is going to be a little project we're going to tinker with throughout the year. I'm going to try different algorithms to see what works better. We're going to mess around with the features. And one also thing to note that I didn't do here was I only looked at single, samples in time and said, what are the frequencies here? I didn't look at anything that's a chain of how the frequencies flow together. That'll potentially help capture how our voice evolves. Like I tend to maybe get excited at the end of a sentence. And there are features of our speech like that you can pick up on with something like a recurrent neural network, which will be a future topic for us. So we covered a lot of ground here tonight, mainly talked about the project. let's summarize logistic regression since that was supposed to be our purpose here. It's basically linear regression. It also involves this logistic curve, so you can do a classification, typically a binary classification.
What's a classification?
Classification is when your output isn't just a number, like in the case of the house, like what's the best price for the house. Classification is like true, false, or isLinhda, is not Linda.
So it's binary?
Usually binary, but you can do some tricks to manage things that are not binary. If it's true that you supply a data set that has a good information content in it, then the algorithm should be able to find the best weights that it can multiply by that input data and run it through that logistic mapping to get this value between 0 and 1 that says how likely it belongs to the class we're interested in.
So logistic regression always runs it between 0 and 1.
Yep. And that's important for classification because ultimately you have to say it's in bucket A or bucket B.
Okay.
And that's why it's slightly different from just a vanilla regression where you'd get a number out. Logistic regression is kind of like your first algorithm you learn when you start doing machine learning, which funnily enough, we've never covered on the show yet. But so there's a lot of topics I haven't touched on. You know, we're almost 4 years in here. We can't do everything, but all things in time, maybe.
Okay, so logistic regression is about you run it through an equation and you get a number between 0 and 1, and generally it can tell you if it's yes or no, an answer to your question.
Yep. It's one of the most simple classification algorithms, but a very effective one too. And it's nice because in theory, those coefficients are interpretable, which means that in the case of our project here of determining who's speaking, I know what the coefficients represent. They represent how much it's relying on each of those frequency bands to predict Linda or Kyle. So in an early attempt when I was working on this, it had the bands it was picking and how it weighted them were like all over the board. There were some low, some high. They were like really noisy, which told me that I had actually overfit the data in that case. So I had to keep working because the values I got intuitively didn't make sense to me. Mm-hmm. And I'll talk more about this in some blog posts, but I ended up trimming it down. That's where I got to the bucketing idea, and that helped a little bit. Now, it's still only, 84% accurate. It's not a great fit, but I didn't necessarily expect a great fit because this is just a simple approach, and it's our baseline now, so we can compare against it as we try other methods and stuff.
So what's another method that you're going to try?
Well, I've already tried XGBoost, which is another mini episode we're going to have to do at some point. That's a good one. It did better. But mostly, I want to get into using deep learning. In particular, I want to try out recurrent neural networks because those are good for data that has some sort of time component to it.
So wait, is logistic regression the beginning of neural networks or no?
No, logistic regression technically doesn't really have anything to do with neural networks, aside from the fact that it's this basic linear optimization using the logistic function.
Is it deep learning?
No. But there are some pieces of it that get used in deep learning. So stay tuned, everybody. I'm going to try and theme almost all the mini episodes for the next couple months around this project. In fact, next time you and I record, Linda, I'm going to have some samples of the mistakes that it makes. So we'll listen to audio where it correctly said, oh, this is Linda talking. And then we'll listen to some of the audio where you are talking and it thinks it's me. So maybe we can learn some cool stuff that way.
Yeah, I should throw my voice more.
What do you think it'll do with the impressions? We got to get good at impressions and see if we can fool the algorithm.
I got to practice.
All right. So we'll go practice. Everyone else will check out the site, and we'll see you next Friday.
Next time.
Before we go, I want to share a quick word from our sponsor this week, which is the Data Science Association. I'm here with Serene, who's going to tell us about an exciting upcoming conference in Dallas in February. Serene, welcome to Data Skeptic.
Hi, Kyle. Thank you so much for having me on the show. We are a Data Science Association, which is a nonprofit organization working to accelerate growth in the data science community. Last year, we hosted the first SoCal Data Science Conference, and it was extremely successful in bringing together 20 guest speakers and 600 data science enthusiasts. This year, we are proud to kick off our Data Science Conference series starting in Dallas. It will be held at the University of Texas at Dallas on February 18th. We have 200 participants already signed up to learn more about the cutting-edge technologies and the developments in data science. We will also be hosting a panel to discuss the talent gap between academia and industry. We have panelists from consulting firms and data science bootcamps such as Galvanize and Metas to share their point of views on what are the essential skills for success in this field. We feel that this subject will be extremely valuable for career changers and students seeking data-driven careers. And right now, we are offering our early bird tickets for $40 only until January 29th. So if you're interested in joining, you may register at dallasdatascience.eventbrite.com.
As an added bonus, the first Data Skeptic listener to email me a copy of their Eventbrite confirmation will get a free Data Skeptic t-shirt. So hurry on over and make that happen. Once again, that's dallasdatascience.eventbrite.com. You can find that in the show notes as well, or at dataskeptic.com. The conference, once again, is Saturday, February 18th at the University of Texas at Dallas.